to practice quiz. Problem number 1, write the definition of the derivative f prime of x and include a diagram. Seconds more. Alright, so the definition of the derivative is f prime of x is the limit as h approaches 0 fx plus h minus fx over h. And all kinds of diagrams can be made, but here's one possible one. As if this is my x, here's my function, and I'm trying to get the derivative right at this point. And that derivative represents the slope of this red line. And h might be this difference here to here, so this is x plus h. And then here is where the corresponding point is. And when you take this is, so this point has coordinates x, f of x. This point has coordinates x plus h, f x plus h. So the change in the y, f of x plus h minus f of x, that just shows up here. Change in the x, x plus h minus x, which reduces to h, that's what's here. This is really change in y over change in x. This is the slope. It's the limit of the slope as this point moves closer to this point. And when we do it the first time, we get the slope of this line, which we say is a reasonable approximation of the slope of the red line. But as we make the h smaller, we get a point that gives us a better approximation. We keep making it smaller, move it closer, we get even better and better and better. So that's f prime of x. Now we go to number 2, write the definition of the definite integral a to b of f of x dx, and include a diagram. Okay, we give you 30 seconds more. Okay, so I imagine if I was in your shoes, I'd be much more comfortable with number 1 than number 2. As a professor, I've taught this so many times that I'm fine with both, but imagining myself as a student, I would probably have a hard time remembering this one. And this integral a to b x dx, formal definition, is it's the limit as n goes to infinity of summation I equals 1 to n of f of x sub I star, it's a little more complicated, delta x. And the picture that's associated with this could look like this. Suppose we're trying to find the area under the curve from A to B. And this is the function f of x. And suppose we start by just dividing this into 4 intervals. So maybe n is 4. And then we would divide it up here, here, and here. And then we would say, alright, if I'm trying to get the area underneath this, I have to pick maybe midpoints or left endpoints or right endpoints of each interval. Those are the typical choices. You don't have to pick one of those. But suppose you picked like midpoints. Then halfway between you'd take here, and then you'd take this, get the area under that rectangle. And midpoint here, that height, get the area under that rectangle. Midpoint, area of this rectangle. And midpoint, area under this line gives you, then this would say is kind of a reasonable estimate of the area. And as we then say, alright, let's make n go to 8, we get a better estimate. And n go to 16, as n goes to infinity, we get more and more precise. And the limit of this goes to this. Now, this is assuming that it's equally spaced in subintervals, and it doesn't have to be equally spaced. So the definition in the textbook's a little different, but I just introduce it this way usually because it's nice and simple, easy to understand. And it's hard enough to remember this after a long period of time. And it was designed, the definite integral, its definition was designed to get areas under curves. And then there are some amazing shortcuts that happen using the antiderivatives and so on. Alright, give me feedback then on numbers 1 and 2, please. Alright, so you all are giving feedback like I kind of expected, and the real intention of this is to review number 2. And I put number 1 because it's good to contrast and to actually, see what you can remember, and these are the 2 primary concepts in calculus. Alright, what we're going to do today is double integrals in 3 space, And so we're going to have to go back to the original definition and then expand on it. And so we needed this review here. And find the average value of f of x equals x squared between x equals 0 and x equals 4.
What does it mean by average value?
All right, good question. When x is 0, the height of the function is 0. When x is 4, the height of the function is 16. When x is 2, the height of the function is only 4. So this function goes up like this. And if it was going in a straight line from 0 to 16, the average height would have been halfway at 8. But it's kind of looping underneath like this. But actually, we can find the exact average value of this, and it's something that was done in Calculus 1. And kind of seeing if you can come up with that idea. Maybe you remember it, maybe you can reconstruct the thinking behind that idea, the concept. So let me give a little bit more time. Okay, 20 seconds more. All right, let me point out that if this was a straight line between these two, then at 8, which is the average value, you would have exactly the same amount of area in this green rectangle as in this red triangle. And that's what it means to be an average value. And this part of this triangle would exactly fill in this part right over here. When it's an average value, the area under the curve is exactly the same as the area underneath the average height right over here. In this case, the average height, we know would have to be smaller than 8 because it was below this line. It's going to be somewhere around here. But this rectangle will have exactly the same area. The green rectangle will have exactly the same area as this blue portion right under here. So the average height get it if we could get the area of the blue stuff. If I can get the area of the blue stuff, and then I divide it by, see, this is a rectangle, and this rectangle is 4 times the average height. So if I can get the area of the blue divided by 4, I will get that, because the area of the green is the same as the area of the blue. And if I got the area of the blue, I've got the area of the green. The area of the green divided by 4 is got to give me the average height. So the area of, we need the area of the blue integral from 0 to 4 of x squared dx is equal to, now this is x cubed over 3 evaluated from 0 to 4, and when you take 4 cubed you get 64. Alright, so that's the blue area. If you take this and you divide it by 4, take this, divide it by 4, it's the same as this, times 1/4. 4 goes into this 16 times, 16 thirds, which is 5 1/3. That is the average height right here. 5 1/3, same amount of area as under that blue curve. Alright, give me a little feedback on this one. Did you remember it? Did you get lost as I was explaining it? How's all this? Okay, and so for me, getting this or not, I definitely would not have remembered any formula. I might have remembered the concept if I had reviewed enough, you know. If I'd have just seen it and then we'd have gone on, I probably wouldn't be able to pull it up later. But if I had it reviewed a few times, I think I'd kind of get the idea on this. Anyway. Alright, number 4. Is the answer a constant? When you figure out a of x, do you get, actually, this wasn't supposed to be there. This is supposed to be there. Is the answer a constant? Twenty seconds more. Alright, my first impulse is to say yes, every single definite integral, since this is from a number to a number, if I have, like, no matter how complicated a function, all I'm going to get is a number. The net number is the area under the curve of this complicated function from x equal 2 to x equal 5. So my first instinct would say, yes, as long as these things are numbers, a definite integral gives me a number. But notice, this is a function of 2 variables, x and y. And this is just an integration
Of y.
of y. And so what kind of answer will I get over here? A function of what variable? X will still be around. This is a function of x. So the answer is no. It seems strange that when we take this, but if we look at it carefully, two variables, we're only integrating and getting that y is going to get replaced by 2, and the y is going to get replaced by 5. And we're going to be subtracting and so on, but you'll still get x's in your answer. Alright, give me a little feedback on number 4, please. Okay, this is a crucial concept in today's lesson. So that's why it's here. Okay, number 5. You need to find the local minimums of a function z equals f of xy. Describe how you find the critical points, and then how you determine if a specific critical point is a local minimum. And do not look at your notes, don't look at anything when you're doing this answer. What can you remember from this, or what can you reconstruct? Okay, 30 seconds more, and then I'm going to ask for a volunteer to do the description. So think about whether you want to volunteer. Okay, anybody up to the challenge? Describe how you find the critical points.
Take a partial derivative with respect to x and y, and set both the derivative is to 0, and solve the system of those two equations. Then the coordinate will be one of the possible candidates for local maximum or local minimum. So we move to second derivative test.
Then you take second derivative test.
Yeah. So how the second derivative and second derivative of fx respect x again, and it behaves whether it's a negative or positive, and it will give you an idea whether local minimum or maximum or saddle point or in conclusion.
Okay, suppose AB is a critical point. So I do fxx. Do I evaluate this at AB?
Yes. For the second derivative part, you have to evaluate those using that the critical point you found out at the first part, and the second derivative as well.
Okay, I find these two. What do I do with this?
And then you find the one of the mixed derivative. For example, fx and the second derivative with respect to y.
Okay.
And then you square it and the subtract from multiplication of fxx and fyy to the respective critical points.
Like this?
Yes.
What else?
Minus fxy at the AB, and on total the thing is squared.
Squared.
Yeah.
Okay.
Yeah. And then that will be our the decision point.
What do we call this?
D of AB.
Okay. And then what do I do next?
If we compare f(x) first, whether it's the positive or negative, and then we
All right, so
we
you
have
can
to
say if fx x of AB, suppose we do this and we find that it's greater than 0.
yes, and then so we continue to calculate what will be the part if the derivative of AB, second derivative of AB will be a positive or negative as well.
Ah, so the
It will be
only
a
way,
long yeah.
if this one is positive, then what would this one have to be in order to give us a chance?
If the D of AB is positive, then it will give the local maximum, right? Local maximum.
This means concave up.
Oh, those are local minimum. I'm sorry.
Right.
This concave.
And this, now if this one's positive and this one's negative, we say we don't have a local extreme. It's more like a saddle point. If this is concave up here, it would have to be concave up here too. Now then, we're concave up, we're likely to be a minimum, but what else has to be true? One other thing.
Critical. Oh, what did I miss?
Then AB is a local min, but there's one other condition that has to be met. Anybody?
Oh, that the first derivative has to be 0.
The first, yeah, that's how we found AB. The first derivative, these two were set to 0, and that told us that this is a critical point.
You need D to be positive.
Then AB, if you have one more thing.
That's what I missed.
Because if these two are the same sign, this will be positive, this product. But if it's outweighed by this, it could bring a f d's greater than 0. Okay, so we still needed d to be greater than 0 because there could be too much twisting involved. And so that's the extra thing that we needed. All right. And that's a great description of how we go about this. And that's it for the practice test. And questions? Any questions on the homework or on anything up to this point?
If the second integral test fails, what is the best method to determine if like a point is a local max or min? Like, do you just have to kind of look at the function and figure out brute force like whether it can ever be lower than a certain value, or is there another method?
Um, you know, that's typically not presented in textbooks. And the answer is, yes, you just got to find some other method of going about it. I would, you rule out the obvious case. If this one is positive and this one, they both have to be either both positive or both negative to have a chance. But if this and this is the case, now hold it. When do you get the case where it's? I think it's when D is 0, right? When D
Yeah.
is 0, then the test is inconclusive. All right, so let's go here. So was there too much twisting to that? I guess probably you'd have to just test some points kind of nearby. You know, if it was me, and if A was, let's say, the point 1,4, I'd be checking 1.1, 4.02, things like this. And if I'm, no matter how close I get and so on, I'm, at an extreme value here, and everything else is behaving, then I could plug in a bunch of points like this. I could try putting it in a 3D grapher and then rotating, but I'd have to magnify on that point. It might be kind of difficult. I might need a 3D grapher that would allow me to, make a dot at a specific point. And then I could zoom in on it and tell. But yeah, there's no like standard method that I know of. Any other questions?
Can we go over 45 from 15.7?
15.7, 45, page 994. Lidless cardboard box. It's made with a volume of 3 cubic meters. Find the dimensions of the box that require the least amount of cardboard. So I have the box. Yeah.
We're probably looking at cube root of 2.
Why is that?
It's a volume versus surface area type deal. So if we take a actually, I'd like to go to a 2D demonstration to make this simpler.
Okay. So now cardboard box, it's assuming that all the dimensions are the same?
I don't think so. I think it's 3 different values.
3 different values. Yeah, because that would, X. All right, let's do it a little more intuitively. let's make this the z, and then the x and a y, something like this. Now actually those last two, I could reverse them, and then they're kind of more similar to if we were in a classroom. And the front corner of the room, I'd point to this corner way back underneath here, and I'd say, here's the z-axis, here's the y-axis, chalkboard's over here, the x-axis comes out at you. So we could get like this. Anyway. And Cameron, you were saying you think you're going to get cube root of 2 for all three?
That's my initial guess. I have a different guess in mind. The other guess is to have x and y be as big as possible while having the surfaces y by z and x by z being minimized as much as possible.
Okay.
I think you've got to recall that it's like a lidless box, and I think that if you include that, I propose like a method for solving it using like a minimization that we'd learned in 2-space.
Okay, now let me pause you for a moment here. I love this idea of a guess to start us off with. Because, and let's go there, and then I'll come back to you in a minute, Ron. If we take all three of these as cube root of 2, then these three are going to get multiplied together is going to give me the volume. And the volume would have to be 4. So I think
I meant to say cube root of 4.
Yeah,
my bad.
That's right. We'll just adjust this to here. Cube root of 4. And I think Rowan is really on track. That would be the case if it had a lid as well. But since we because the amount of surface area is the same as the amount of cardboard except for the surface of the lid. So what I'm going to anticipate is that we're going to have a bigger base. This can be bigger, and these, I'm going to exaggerate it, can be smaller, because why can we make this smaller? Because we only need one of those surfaces. We don't need the top surface. So we can afford to make that one bigger, and we can get more volume in it. All right. So that's some basics. And Rowan, what was your proposed solution?
Well, I guess the way I wrote the equation for this, situation, is I started with two equations. The first one represents the volume, so it's just x times y times z is equal to 4.
So this is x times y is equal to 4. This has to be true no matter what. Sometimes we call this a constraint. You don't get to change this. This has got to be true. Okay? And then, keep going.
So then the surface area, which is going to be a different function, it's going to be...
So this is volume.
Yeah, that's for volume. And then the surface area function is more complicated. It's going to be, in this case, y times x, or x times y, for like the bottom piece.
Okay.
And then we get 2 z times y for the two sides, and then 2 x times z. And then you can express that latter function in terms of just two variables by...
All right, so this is what we're going to call, let's say, S for surface area.
Yeah, sounds good.
Okay. And then...
So I guess from this point, I I took the volume function and I said like, x is equal to 4 divided by y times z.
So what you did is you solved for x.
Yeah, I can't remember exactly which variable I used in the homework, but
And then
it's
substitute that into this equation. And then that new equation will only have s in terms of 2 variables instead of 3 variables. So then this s would be a function of y and z only, because the x had been replaced with y's and z's. Okay? And now, how does that help us, Rowan, having s in terms of y and z instead of x, y, and z?
well, it's a rather lengthy process from here, but that's exactly the problems we've been doing last class. It's just, minimizing.
That is identical to the problems we were looking at over here, which was, here is a function of 2 variables, find extreme values. And so to maximize or minimize the surface area, we would then take that function. All right. So, Matthew, is that enough?
Yeah, that makes sense.
Okay. So we'll stop with that. And any other questions? All right. Let's start with double integrals over rectangular regions. A single integral, like the integral from 0 to 4 of x squared dx, found an area. And we actually even found the average value of x squared in the interval 0 to 4 by using this. Okay. We will use a double integral to find a volume. Area under a curve will be replaced with volume under a surface. Okay. So, and here are some images right from the textbook. We'll use a double integral to find a volume. All right. So, here we're going to be in this section, double integrals over rectangular regions. Now in the following session, we'll lift the restriction that the region in the xy plane had to be rectangular. But we start out with something nice and simple, where the region in the xy plane is a simple rectangle. So here you have this surface, and what we're going to wind up doing is dividing up the x-axis into a whole bunch of little pieces. And the same thing with the y-axis, divided up into a whole bunch of little pieces. And instead of pictures like this, where we have little rectangles that we're finding the area of, we're going to wind up with little columns that we're going to be finding the volumes of, and we're going to add them all together to get the volume of this hole underneath this surface above this rectangular region. Okay, it'll have similar consequences as when we did integrals in Calculus 1, is that if you go underneath the xy plane, that'll count as negative volume, and that'll cancel out some of the positive volume if you're also above and below the xy plane. Alright, we'll do all our pictures as if everything is above the xy plane to just get the basics of the idea. Okay. And so we see dividing up the x, we might go from A to B along the x-axis, from C to D along the y-axis. And then You know how we used like 4 subintervals along the x-axis and maybe 4 subintervals along the y-axis, and then it just carves out all these little tiny rectangles. Okay. And then we were using x sub I star when we were in 2 space, and now we're going to have, as this shows down here, x sub k star and y sub k star as a point in the kth rectangle. It's going to be, it could be, now there's more choices now. We had typical choices before were left endpoint, right endpoint, midpoint. Well, we could take, more typical choices might be in each little square. Lower left-hand corner, lower right-hand corner, upper left-hand corner, upper right-hand corner, or midpoint of the entire little square. Those are kind of more of the typical choices, but it could be anything. It doesn't have to be one of those choices. Okay. And it says we use simple surfaces to demonstrate the relationship of the double integral to volume. Okay. And so we had looked at the definition of a single integral. The single integral, its definition, it was created to find areas under curve. Similarly, double integral, its definition was set up to find volumes under surfaces. So, definition of double integrals. A function f defined on a rectangular region R in the xy plane is integrable on R. So it means you can integrate it and get an answer if this particular limit exists for all ways that you partition R. Now, partitions of R means you divide up along the x-axis from A to B, divide up along the y-axis from A to B, and you make all these little subrectangles. For all partitions of R, and all choices of x sub k star, y sub k star within those partitions. Okay. The limit is the double integral of f over r, which we write like this. Now, notice what's changed. Fundamental changes are, we don't have delta x anymore. We have this. Delta x replaced by this. Now, this delta a sub k is going to be the area of one of these little rectangles in the xy plane. And it's going to be coming from partitioning the x-axis, partitioning the y-axis, these little parts, delta x sub k is that little difference, delta y sub k. So this delta a sub k is going to be delta x sub k times delta y sub k. And thus you see why it's going to lead us into a double integral, because you're going to have to be integrating along x and along the y. Okay, but this is the terminology the textbook uses, which is the most generalized. The stars can be any points in the rectangle. It doesn't even have to be consistent from one rectangle to the next. You can take midpoint on one rectangle, and the next rectangle pick the lower left-hand corner. And the next rectangle use the upper. You can do anything. It doesn't matter, because you're going to take the limit. Now the del down here is the biggest sub-area, the largest of all the delta a sub k's. And as long as that goes to 0, then that's going to force finer and finer partitions. And then you take a sample point in each subrectangle. When you take the area of the base times that sample point, now that sample point will be the height of the column. And then you multiply the area of the base times the height, and it gives you the volume of that column. So hopefully it's making intuitive sense that this is a way to get the volume underneath the surface. And when you take the limit, you turn approximations into exact answers. Alright, so first thing we're going to go over, well, hold it, let me state how other textbooks start out by defining the double integral as they use two variables, m and n. And both of these go to infinity, and you have a double summation, x sub I, x sub j, delta a. And you don't have to put a subscript with the delta, because you require where the rectangle is divided or partitioned into equal subportions of delta x and delta y. So if you require them to be equally spaced, and I like that idea of introducing it first that way, because, technically this is correct, because you don't have to make them equally spaced, and you don't have to be consistent in how you pick this stuff. But if you imagine it starting out that way, it's easier to get the basic concepts.
Okay, that part, what do M and N stand for?
The M and N, okay, they are the same kind of thing that when we did this, we take N is how many, if you divide the x-axis into 4 equal regions, like we did here, then the N is 4. And so then you're going to say, sum up from 1 to 4, all these, the first a point in the first subregion times the delta x, and so on. So it's the same, N is along the x-axis, and M is along the y-axis. Does that answer your question, Isu?
Yes, yes.
And then, note also, x sub I, y sub j star is a sample point in the domain. Now, here's one possibility. If you say that x sub I star is going to be x sub I, and y sub j star is going to be y sub j, then we would be choosing the sample point to be the upper right-hand corner of each little box in the xy plane. Now, why this is the upper right-hand corner is because, let me just show you real quick, if I had my region here, see, here would be x0, x1, x2, here's y0, y1, y2, and we are dividing up the subregion like this. Now notice the summation starts with 1, not with 0. Although these start with 0, this starts with 1. So if you said x sub I star, so the first one is you're going to use x1, you're going to use this in the first region. And then you're going to use this in the first region. If you take x1 and y1, it's this point in the upper right-hand corner that you're picking. If you had put a -1 underneath these, then you'd be picking the lower left-hand corner of each subregion. Okay. Any questions? when we take the limit and become an integral, delta A becomes dx dy, or dy dx, depending on which order you wind up setting up. Thus the need for the double integral. Alright, so we're gonna take a break right now, and when we come back from the break, we'll do this problem number 2. And so we will start again. At 6:42 p.m. And does anybody need to speak to me before I take my break? All right. we'll start up again. And, alright. So, the rectangular region is negative 1 by 3 on the x-axis and 0 to 2 on the y-axis. So I'm going to draw a picture of this. Negative 1, 2, 3, and 1, 2 on the y-axis. And we're going to I'm not going to draw this function at all. I'm just going to draw a rectangle in the domain. And notice I didn't put a z-axis. And I'm getting the x and the y in the most comfortable format that I'm used to, rather than that 3D kind of image. And then now it says use m equals 4. M is how I guess m comes before n. So m is for the x. I'm going to divide the x into 4 equal subregions. Now the length from negative 1 to 3 is 4. Divide that into 4, each is 1. N is 2 for the vertical, so that's also going to be 1 with 1. Alright, and we're going to estimate this integral. So the integral, double integral over r of y squared minus 2x squared dA is equal to, now it says take sample points to be the upper left-hand corners of this rectangle. So I'm going to take this point right here. Now this point is negative 1, positive 1. So that's the x value, that's the y value. So I'm going to be putting those into here for this. I'm going to take, now when I take f of negative 1, 1, times the delta A, and then I'm going to move to my next rectangle. And I could move horizontally and go through like this, or any which way I want to do it, but I have to go through every sub-rectangle and find the f of the upper left-hand corner point. All right. Now, let's just do one more. If I go to this one, it's 0 over 1 up plus f of 0, 1 times delta A plus da da da. Now, when I do f of negative 1, 1, I'm going to I plug it into this. My function is this. So f of negative 1, 1 is 1 minus 2, which is negative 1. And delta A is, well, every rectangle has width of 1 and height of 1, so it's 1 by 1, so it's 1. And then f of 0, 1, plug in 0 for my, 0 for my x, 1 for my y, and I get 1. And you just keep doing this for each of these points as we go through. Now, this looks a lot different than what I was describing over here. We could be making this image kind of like that. It would be looking more like this. And we'd be making this rectangle down here in this XY plane, and then we'd be having this surface above that rectangle, above or below the XY plane over here, and so on. We could be doing that, but notice we don't need to get this answer. All right, any questions? All right, I'll assume everything's good, and we'll move on. A 20-foot by 30-foot swimming pool is filled with water. The depth is measured at 5-foot intervals, starting at one corner of the pool, and the values are recorded in the table. So the X values are here, and the Y values are in this row over here. Estimate the volume of the water using the midpoint rule, that M is 2 and N is 3. Alright, so I'm going to turn you loose on this, and I'm going to give you a couple minutes to get as far as you can on this, to really figure out what you're supposed to be doing and how the process is going. You don't have to get super far into it, but you got to understand how to do it. Alright, so at a certain point, I'm going to have you check in with your group members, but just work on this individually for right now. Okay, so go to your group chat and just check in with your partner. Just ask, do you understand what's going on? And put your kind of ideas down. And how in the world would you get going on this problem? I'm going to ask the group in a little bit. group 1, how might I do this thing? How to proceed?
One way, or one idea I had is you could kind of rewrite the table, but you cut off one row and one column, and you fill in each value with like the average between the values around it. So like the first value that I'd put in like maybe the upper left would be like 3 because it's halfway between 2 and 4, and then because it's like also halfway between 3 and 3, if that makes sense, because that's what's one below it. Because the one below it would also be 3, and then that would combine to be. So it's like almost like the corner of the top 4 cells is 3.
Oh, okay. So what you're kind of doing is breaking these top 4 into one group. Is that right?
Well, not exactly. Basically, first I rewrote all of the columns, combining the ones on the right and the left into a single value, and then the next step would be to rewrite all the rows, combining the top and bottom. So yes, technically you're looking at those 4 values, but the next square would overlap that rectangle.
Okay. And that was the problem that you were having was with the overlaps, right? And so you wanted to get rid of the overlaps, and by getting rid of the overlaps you used things like 2.5 right in the middle here. Am I interpreting you right?
Well, I actually used 3 right there.
Why 3 instead of 2.5?
Well, I mean, it's 3 is the average of 2 and 4. So like you could say like 4 plus 2 is 6.
Okay. So you're not taking these numbers on this column. You're just taking these numbers.
Yeah.
Okay. And you put a big 3 kind of here?
Yeah, my method is very laborious, but
Okay. All right.
yes.
So that's one way to approach this. And let me see if there's anybody else that had another way to look at this.
So I didn't get all the way through, but kind of going with what we did in that last problem, since it said we had m equals 2 and n equals 3, I kind of made the table into one smaller table with 2 columns and 3 rows.
Ah, okay. X's down this way, and alright, Y's over here. And what'd you do for your X's?
Well, so I assumed that the m was for the x, and so since that was 2, I just split it in half, and so I had so I drew it as like with the points we had in the last one. So like on the left point you'd have 0, in the middle you'd have 15, then on the far right you'd have 30. Because I drew it as more like that, like what the table we have over there.
Like this? If this is the Y's, you just went from here to here to here?
Yeah.
And the X's 0 to 10 to 20?
Yeah.
Okay. And then, how'd you fill these things in?
Actually, so the X's would have 3 different sections, not 2.
Oh.
It's like with 0, I kind of drew it as like So I'm not really too well.
Ah, alright.
I didn't really finish, and so I kind of got stuck, and so I'm not really too
So
sure.
the x's go from 0 to 20. If we make this on a normal x, y axis, ten, 20, 10, 20. The y's go all up to 30. 30. Okay. And then depth is measured at 5-foot intervals. Now we're going to use the midpoint rule, m equals 2. So we're going to divide the x-axis into 2 subregions right here. So that's 2. And the y, n equals 3 for the 30 foot into 3 intervals. Okay, and then use the midpoint rule. Estimate the value using them. So what we need is the height at this center point. 5 is 4. We don't do an average. We just use this number 4 for this rectangle. Is everybody following? And then the midpoint of this one is when the x is 5 and the y is 15. X is 5, y is 15. We're going to get that one. And when the x is 5 and the y is 25, we get this one. So we use those 3 values right here. And then over here, when the x is 15 and the y is 5, we're going to go here. And when the x is 15, the y is 15. We're going to have this. When the x is 15, the y is 25. We get this 7. Now, estimate the volume of the water using the midpoint rule. Volume is going to be approximately. Now, my function is, we only have the table values. We don't know what the function is. But remember, the first value was 5 times the area of that piece plus f of 515 times area of that piece, and so on. And the area each time, these are 10 by 10 regions, 10 wide, 10 high. So these are always 100. And it's actually square feet, 100 square feet. And that's also the volume of the first foot in height. And then this first one is 4 feet high. So this volume we're going to be getting is 4 times 100 plus 5, if we go vertically, times 100 plus, and I'm going to factor out the 100s. and make it, it's just going to be adding all these up. 4 plus 5 plus 10 plus 3 plus 5 plus 7. The volume is approximately, now this is 10, 20, 34, 34 with 2 zeros, 3,400 cubic feet. That would be my approximation if I followed these directions. There. Alright. Give me a little feedback on this. Did you get lost? Or did you follow this? It makes sense.
Wait, so can you clarify why delta A is 100?
It's the area of each subregion, and each of these is
Oh, I see. That makes sense.
10 by 10. That's right, 10 feet by 10 feet. Any other questions? Yeah, language is difficult. What in the hell are they asking me to do? An oddly built swimming pool. Isn't that incredible? It's all these little subsections, because like the water tends to want to be the same level. Actually, it's what's the pattern of the pool? So, you know, the top of the surface of the pool is going to be, you know, the same height, and they have different depths at different spots. And yes, at this end of the pool, if you can kind of think of it, that it's all this standard, but it's shallower over here. That's a good comment. And then it's kind of strange over here. So the bottom of the pool is very strangely shaped. Okay. And, all right. Now this is getting us used to this basic definition of a double integral. It was set up to find volumes. Now, none of the homework problems are going to look like what these problems we just did. This textbook doesn't tend to emphasize that. This textbook jumps right into these iterated integrals. So this is what's related to the homework, but I strongly feel that you need to have a sense of this definition first before you go into this to really understand this well. So, iterated integrals. Assume f of x, y is greater than or equal to 0, so a simple volume interpretation of the double integral. The pieces of area came from rectangles in the domain. Now the pieces of area, in this situation, we're going to change things up. Now, the pieces of area are between planes, planes twice, parallel to the xz plane and to the yz plane. So let me zoom in. This is a picture from the textbook. So we have a surface, and we have a rectangle in the domain, and we're finding the volume underneath that surface. The surface is kind of like looks like a transparent, tarp up there. Now, I'm going to kind of think of this as a strangely shaped loaf of bread. Okay. If a solid is sliced parallel to the y-axis and perpendicular to the xy plane, and a cross-sectional area of the slice of the point A is A sub x, then the volume of the solid region is, the integral from A to B of A sub x dx. Now, What I just read here is probably incomprehensible at that pace. Let me break that down to make sure that you understand that. Now, for a single slice, we're going to find the change in the volume of a single slice. Now, a slice is vertical, so it's a vertical slice parallel to this XY plane is kind of like the guillotine that comes down whoosh, and slices off a portion of this bread. And for that single slice, if that slice is thin enough, the volume of that slice really depends on two things. The area of, let's say, that purple portion. If we could somehow get the area of that purple portion and then multiply it by the thickness of the piece of slice, delta x, we would have this little volume of that one slice of bread. And then if we put them all together, we get the total volume. And so it's kind of depending on the area and the dx, and it's going to turn into an integral. Okay. Now, the problem with finding a sub x, the area of this purple region, it's a two-dimensional region, is twofold. It seems to be a complex area of a face. We call that a face. The guillotines come down and slice off a piece of bread.
It looks like a sine function in both the x and y direction.
Ah, so actually, in the x and y direction, this shape of this curve right here would be critical to get that area. That's right. And it kind of looks a bit like a sine function. It seems to be a complex area of a face, and another problem is it is constantly changing. When x changes, as you move the x from A to B, as you move along here, if an x changes even a tiny bit, the a sub x, the area of the face, also changes. All right, so we have two problems we have to overcome if we want to get the volume of this. Both of these problems are solvable. First, let's find a sub x for a given fixed value of x. Now, this is critical that we're going to fix a certain value of x. We take the x and we hold it fixed while we find the area for that particular value of x. Since x is fixed, y is treated as the only variable. And the area of this face is a simple area under a curve problem. The area a sub x is the integral from c to d of f of xy dy. So here's c, here's d. We're going to integrate from c to d, and then although this is a two-space, now this is a three-space function. That clear surface at the top, we follow that up and we follow that down. If we hold the x constant, y is the only variable, and we get this right here, and that will represent the area of the face. Okay. Now, as for the problem of a sub x constantly changing, recall from the earlier practice quiz problem, the integral from c to d f of xy dy returns a variable. Remember, we said it was a function of x, not a constant. Because this will have x and y's in it, the only thing that's going to be replaced is the y is going to be replaced by c and d, and it'll still have x's in it. It's a variable, not a constant. It represents the area of the face, and it is continually changing as x moves from A to B. So as x goes from A to B, as we move along here, the area of each of these purple faces is going to get constantly updated because it's a variable that we're going to get here, not a specific constant. All right. Thus, volume V is the integral from A to B of AX dx is true when we look at the entire loaf of bread above. We just go from A to B, and if we could have this great function that always represented the area of the purple face as we move from here to here, this would give us the volume. That's true when we look at the entire loaf. And also, we just found out that the area for a single slice, when you hold x constant, turns out to be from C, the integral from C to D of f of x dy, gives us the area of individual slices of bread. So we have this formula that's true, and we have this formula that's true. This is an integral along the x. This is an integral along the y. When we substitute this second formula into the first, so when we see this a sub x, we replace it with this. We get v equals integral from c to d, and then parentheses, this integral inside that other integral, dy. Now, when the textbook writes these double integrals, they get rid of this parenthesis here and here. Math likes to do as little bit of writing as possible, and they just make it convention that, like, all right, pretend there is a parenthesis there when you see this, so we don't have to write these parentheses. Right. And so, thus, this volume not only could be estimated by using, rectangles and so on, but it also, we can get that volume by also doing what we call an iterated integral, or a double integral. Iterated means one inside the other. And there we have it. So, that's the theory on why this double integral also gives us the volume under this, just as good as this other thing does. So it's similar as in Calc 1 when we did an integral, and we did it with, partitioning the interval into these different parts, and then, estimating it. And then we jumped into, there's a faster way, and that was with the fundamental theorem of calculus, using an antiderivative. Same thing, we start with the definition, and then we jump to this double integral, giving us the same result. Alright, so, example. Let's find this integral after first estimating the result. And let me pause here for a minute. Any questions, on this theory before I go to this example?
Is it coincidental that double integrals have a commutative property the same way that double derivatives do?
We're going to find out that, great question, Cameron, that if you reverse the order of these things, you get a different answer. And they do not, it's not commutative. So fxy and fyx are equal, but these integrals, it's very difficult to commute the order. And if you change the order, you get a different result. All right, so
actually, I have a quick clarification. I'm sorry. So, can you go up a little bit? So I'm confused. Here it looks like the volume is like the integral from C to D of the integral from a to b of f of xy, is that using the same notation as above? Because there we've got that ax is from, or that ax is the integral from c to d of f of xy. So, or no. I just want, like, are they switched?
Yeah, I think you're right. I think I screwed up. This C to D has got to go inside.
Okay.
Thank you very much. This is D, and this is C, and this is A to B. Way to catch that, Rowan. And this, you got to do the Y first, and then the X. Okay, that's now correct. Okay. And Cameron, of course, you would think it's commutative because I switched it around and said it was still the same, but it's not. Okay. All right. So now we come down to here. Any other questions before we come to this example?
I have a follow-on question after the example, and probably best after the class.
Okay, great. All right, so let's...
So I have just a simple question about the loaf of bread, the picture. Maybe I misunderstood when you're talking, but did you say if you fix x
Yes.
and move around along the y-axis,
Yes.
the area will change, right?
If you fix the x temporarily,
Yeah.
so freeze time for just a moment, and then you can find the area of this face by having the area is the integral from C to D over here. Okay, and then you got to quickly unfreeze the x to let it move, and then you're always going to get an answer in terms of x over here.
And in that case, when you move, when when x is free to move around, that means y is fixed, right?
Okay, I don't think we need to do that though. We need to, and in fact, when you have it in this order, you start with a double integral written like this. Is you think of x as starting out at a, and then while x is at a, or very close to a, then the y goes through all its values from C to D. And then the x moves up a tiny bit, and then the y goes through all of its values from C to D. And so that's how we think of this. If we think of movement happening in here, is x is at A, and then we find the area of the face, and then we multiply it by a tiny little bit, a tiny thickness, and then we move along. You know, we found the area at the first 1/10 of an inch thickness, and then we move to the next little bit, and then we go here, find the area of that face, multiply by 1/10 again, and then so on, and we keep moving on.
Yeah, and so my simple question was, in case if you fix y and move a little bit x to the next position, I thought that you said that the area of the cut surface of the bread will change. Is that what you said, or did I misunderstood?
Every time the x moves a little bit, then you get a new surface, which could be a little bit different area. Yeah.
From the looks like if if you fix the y and move the x, I thought that the cut surface basic area will not move, only thickness.
All right, you don't need to fix the y to move the x. It's better to think of it as you start the x somewhere and then you run the y through all its possible values between c and d and get this
Okay.
there. And then don't think about fixing the y. Then you move the x and then you do the y through all its possible values. The y doesn't need to be fixed because the x is coming out here and it initiates the action. The x, you start at x is a, and while x is a, find the area of the face, and then so on. And then go to the next. And the y constantly just goes from here to here, but it starts up again every time you move the x a little bit.
All right, I got it. Thanks.
You're welcome. All right, so now let's do this integral, but first we're going to estimate the result. All right, to estimate the result, I'm going to think of it like this. The x is going to be going, so the amount of this and this go together, while this and this go together. How do I know that? Because it's really a parentheses was left out. It's really this integral is inside that. Okay, so the x is going from -1 to 4. The y's are going from 1 to 2. And so the region in the domain is right here. Now, the surface is this. Now, this is going to be an extremely crude estimate, but this, let's find, now the area of this is height of 1, width of 5, 1 times 5 is 5. So the area of this red rectangle is 5, and let's just multiply it by an average height. The average, if I take the volume, is approximately this area times average height. And so it's going to be 5 times, now let's just get an average height from here to here. Now, when I plug in numbers really close to 4, I'm going to get something really big for x. You know, x can range from -1 to 4. But the y doesn't really, y is even more important than the x because the y gets squared. Alright, so for an average value of x between -1 and 4, we'll add these two together, 3, divide by 2, 1.5. So let's pick an input x of 1.5. Now, what's the average value of y squared when y goes between 1 and 2? Well, 1 squared is just 1, but 2 squared is 4. So what's kind of halfway between that, you might put, you know, a y value of a little bit more than the halfway point, so that you'd get an output, you know, a little closer to 4 than to 3 or something like this. So instead of 1, I might pick 1 point. Instead of 1.5, I might pick like 1.6 to get a little bit lower. So it could be 1.5 plus 1.6 squared. And then that's going to be 5 times, and let's punch this in our calculator real quick. And I get about 91.4. I forget what that result. This one, oh yeah, this was like 18.28. And I get like 91.4. So I'm going to estimate that the volume is approximately 91.4. So that when I do this, I have something to compare it to say, oh, this makes a little bit of sense or it doesn't. If I get a volume that's like -6, I would say, hey, something is really strange. I didn't understand this right. Okay. So now, any questions on my approximation of the volume? All right. Now let's do.
Sorry, I missed why we were going with 1.6 on the y-axis.
Okay. So I could pick a reasonable choice. Could have also been 1.5 because the average y value is halfway between these two. But
okay.
But I chose one a little closer to 2 because when you square 1, you only get 1, but when you square 2, you get 4. So the average outputs vary between 1 and 4, so I used a number a little bit bigger.
Okay. There.
All right. So now that's my estimate for my volume. Let's figure out the exact double integral. The integral from -1 to 4. Now when I write it out this first time here, I'm going to put this parentheses. Alright, and when you have nested parentheses, we work from the inside out. So we're going to do this integral on the inside. So that means we leave the outer integral there. Now how do you do an integral? You take an antiderivative of this. Antiderivative of x with respect to y is xy. Because if you take the derivative of this with respect to y, you get back to x. So x is just a constant with respect to y. Now this is conceptually that idea of, remember, we hold the x constant as we move across the loaf of bread, and then we find the area of the face. So we get this plus the integral of y squared dy is y cubed over 3. And then this, that's the antiderivative of this. This gets evaluated. Now, if I just put 1 to 2, I'd be really making a big error there. Because it's the y that goes, not the x. Y equals 1 to y equals 2. And then, after I get this, then I have my dx that I have to compute. Any questions here? So then, let me continue. -1 to 4. Now, when you're doing this stuff, a lot of people will do the following. They won't write down this and keep dragging this -1 to 4 all along. They'll just, at this point, they'll do something like this. They'll put a box around this, and they'll write timeout, and they'll just figure out what that integral is. So they don't have to keep dragging around the other symbols. Now we'll eventually get to triple integrals, and then that becomes even more of a preference later on. And then you do a little timeout and you put a box around all this, and you get your answer, and then you come back in and replace that with that. So that's an alternate way of writing this stuff out. So now I'm going to evaluate this at 2 for both cases. And when I plug in 2, I get 2x minus 8, or plus 8 thirds. minus, and then I evaluate it at 1. When I evaluate it at 1, I get x plus 1/3. And then dx. All right, now remember, this represents, the inner one represents the area of the face. But we had said the area of the face doesn't give you a number, it gives you a function of x. And there it is. It's totally x's. All the y's are gone. They've been replaced by those constants. And this thing that I'm going to get inside this parenthesis is the area of the face, but as a variable. It represents the area of the face of this thing in variable terminology as we move the x's from -1 to 4. So let me simplify this. 2x minus x is x. 8/3 minus 1/3 is 7/3. This cool little thing represents the area of the faces for this as we move along. Now this becomes a nice easy integral from Calc 1. Antiderivative of x is x squared over 2, and antiderivative of this, 7/3 x. Evaluated from x equals -1 to x equals 4. Now, let's remember my approximation for the total volume was, I thought the height of this surface, average height, was about 18, so total volume is about 91. Let's see if I get anywhere close to that. And this is going to equal, now we plug in the 4, I'm going to get 16 halves plus 4 times 7 is 28/3 minus, and then when I plug in -1, I get 1/2 minus 7/3. And putting this one and this one together, I get 17 halves. No, 15 halves. Putting this one and this one, double negative makes positive. 28 plus 7 is 35/3. So that's 7.5 plus 33 is 11 2/3. And that's 18, 19, and what is that? 3/6 plus 4/6.
Should be 1/3 left.
I think it's going to be 1/6.
Oh yeah.
Yeah. 3/6 and 4/6 is 7/6. Oh, you get 1/6. All right. So I got 19 and a 6. Let's look back. That's not consistent with my estimate of the volume. So either I made a mistake in my computations, or I made a mistake in estimating the volume over here. And now I could check this by plugging this into like a graphing calculator or like Wolfram Alpha, and I don't know.
Well, isn't it more likely to be the estimation that is incorrect because
That's right.
Because by definition, an estimation is not a precise answer.
But it shouldn't be this far off. Okay, and I think 1.6 squared, I think this 18.28, I screwed up with my calculator. Well, let me do that again. 1.6
That's 2.56.
plus 1.5. Yes. All right. This,
Order of operations, not supported on some calculators.
so this was really 4.06. 4.06 times 5, 20.3. Now that's very similar to this. Voila! And I have this. So now I feel very comfortable that I got an answer that makes sense. Any questions or comments? All right, let's go to the next one. We won't have time to finish this. Let me give you a minute to estimate the result first. This is tricky, hard to get used to. Let me give you a minute to work on that, and then I'll do that. Alright, so my x goes from -1 to 1. And my y goes from 1 to 2. So this is my region right here. Now, the volume is going to be approximately the area of that base times the average height. And this is a 2 by 1 rectangle, so its area is 2. The average height is always the trickiest. Now, let's just find out the heights at a few points, like right here. I plug in 0 for the x, and I plug in 1.5 for the y. And so it would be 0 squared plus 1.5 squared. 1.5 times 1.5 is it 2.25? Okay, that would be the height right at this point, right here. Alright, and then let's take another height. Let's kind of go along the midline. You went here. So you'd be plugging in 1 for the x and 1.5 for the y. Now the x's vary from 1, x squared will vary from 1 to 0 to 1. And the x squareds, their average value might be, I don't know, about 0.5. The y squareds, their average value would be from 1 squared to 4. Again, maybe I'd pick, instead of halfway in between, a little bit on the bigger side, 1.6 squared. Okay, so if I did this, so then I'll do this a little more carefully than we did last time. 1.6 squared plus 0.5, 3.06. So around 3. So, and then I'm going to get my volume is about 6. That's my estimate. And then I'm going to do this double integral. Now I'm going to go ahead and jump right into doing this. This part I integrate with respect to x. So antiderivative of x squared is x cubed over 3. And the antiderivative of y squared is y squared x. So when I take its derivative with respect to x, I get y squared. This is from x equals 1 to x equals 2, then dy. So then this is integral from -1 to 1. When I plug in 2, I'm going to get 8/3 plus 2y squared minus, when I plug in 1, I'm going to get 1/3 plus y squared. Now all of this gets multiplied by dy. There's just a function of y now. And then this is the integral -1 to 1. 8/3 minus 1/3 is 7/3. 2y squared minus y squared is plus y squared dy. And then that integral of 7/3 dy is 7/3 y. This integral is plus y cubed over 3, evaluated from y equals -1 to y equals 1. And then when I put 1 in, I'm going to get 7/3 plus 1/3 minus, and when I put in -1, I get -7/3 minus 1/3. And that's going to give me 14. Now this is, yeah. If I put that one and that one together, I get 14/3. That one and that one together, I get plus 2/3, which is 16/3, which is 5 1/3. And was that close to my approximation? 6, sure is. There's my result. So the homework is 16.1. We will stop here. And Cameron, you wanted to talk to me? So we can wait a minute until others have hopped off.
Okay, thank you.
Thank you.
Thank you.